Hello everyone, I am Melissa Afrina binti Muhammad Aidi from BERG FTKEK. Today I will present our complete solution for the Smart Irrigation Control System assignment under BERG 1413. To start, let's look at our core system configurations. The operational status of our irrigation pump P is handled by monitoring four key digital input variables. First, we have O, which represents the manual override switch. Second is D, which is our day and night sensor. Third is M, which tracks our soil moisture level. And fourth is T, which stands the ambient temperature. Our output target, P, turns on at logic level 1 and shuts off at logic level O. Next, we translate our real-world specifications into a complete 16-row truth table matrix. Our system operation follows strict priority constraints. The first major rule dictates that the irrigation pump activates automatically during daytime hours only if the soil moisture is low and the temperature is high. This maps strictly to state 5, where O is 0, D is 1, M is 0, and T is 1. Under any other automated states, if the moisture level is sufficient or if it is night, the pump remains safely off. However, our second rule establishes that the manual override switch, O, has absolute priority over the entire system. Therefore, whenever O equals 1, corresponding to states 8 through 15, the output pump is instantly forced to activate regardless of any environmental sensor values. To simplify this truth table into an efficient hardware layout, we plot our active output states into a 4-variable Karnaugh map using gray code formatting. By analyzing adjacency, we form two distinct optimization loops. Our first loop is a size 8 octet that groups state 8 through 15. Across this large block, variables D, M, and T alter their state boundaries completely and cancel out, leaving us with our first table term, O. Our second loop isolates the automatic trigger by combining state 5 and state 13 vertically into a size 2 pair loop. Looking horizontally, columns fix this group to M' and T. Vertically, variable O cancels out while variables D stays constant at 1, yielding our second product term, D, M', T. Based on our assignment criteria, our derived simplified Boolean expression for the system is P equals to M' TD plus O. This means our irrigation pump P will turn on under two main conditions. First, automatically, if the soil moisture M is dry, which is represented as M', the temperature T is high and it is daytime D. Second, manually, if the manual override O is activated by the user, which bypasses all environmental sensor rules. To implement this design inside Protus 8.17, we have structured our digital logic gates in a clean left-to-right hierarchy. On the far left, we use four interactive logic state inputs representing our environmental sensors O, D, M, and T. For our processing stage, sensor M passes through a 7404 NOT gate to get our inverted state. This output is combined with inputs D and T using a 7411 3-input AND gate. Finally, the automatic product branch merged with our manual override line via a 7432 2-input OR gate, which connects directly to our output display, the logic prop P.
Today, I will explain how this digital logic circuit works. For the inputs, O, D, M, and T are switches that can be on or off. These are the signals that control the circuit. The M input first goes through a NOT gate. This means if M is on, the output becomes off, and if M is off, the output becomes on. So the NOT gate inverts the M signal. The AND gate combines three signals, D, T, and the inverted M. The AND gate only inputs on when all three inputs are on at the same time. The OR gate then takes two inputs, the O switch and the output from the AND gate. The OR gate outputs on if either O is on or the AND gate is on. Finally, the OR gate's output goes to the indicator. This means the indicator will light up if O is on, or if D and T are on while M is off. In short, the circuit lights the output when O is active or when D and T are active together while M is inactive. This shows how combining NOT, AND, and OR gates can create a specific control logic.